Welcome to the next video in our networking series, and again we're still looking at the application layer here, but this time we're going to be looking at some of the housekeeping protocols, that hidden glue that binds our networks together. So before we get started, let's have a quick review of what we did last time. So we looked at HTTP, FTP and SMTP. Well, I asked you to go away and look at SMTP, and fingers crossed, touch wood, it went smoothly. So like most of these protocols, the basics is normally pretty easy to understand. So for example, what commands does SMTP have? But as you should have found, there's a lot more stuff going on with mail delivery. How an email leaves your client and is pushed onto that network and passed through those various mail servers. We will be looking at in more detail in the lab, so we'll be sending some emails between our Raspberry Pis and the lab's email server. So you'll see this in action, capture some packets in Wireshark. But the key thing here is I just wanted you to go and look at some of those RFCs, start to do that background reading, identify what the structure of an RFC looks like. So if you need to go and do a little bit of research on other protocols, you'll know how to get started. And we'll be doing that obviously as we go through this module. So as I said, in this lecture we're going to be looking at some of those housekeeping protocols, those background protocols that allow the internet to function. The main one being DNS. So IP addresses are fine for computers to identify other computers on a network, but from a human point of view, we'd like to give each host a name. And that's what we do. So if you obviously look at a web page, you'll see there's the host name and a domain name, and that needs to be converted into an IP address. And the way we do that one is with our domain name systems, DNS servers. So these servers can run different flavors of software, but a common one is the Berkeley Internet Domain Name Software, or BIND. So you can configure your own DNS server using this software on your own machines if you desire. Another common tool is DIG, a domain information groper, so a tool that will allow you to query these DNS servers. So you can manually look up these various domain names or these DNS servers, or do a reverse dig. You can convert an IP address into a domain name. Finally, we'll be looking at how a host is assigned a IP address. So when you connect a computer to a network, how does it get the IP address that it needs to communicate with other hosts on the network? And there's two main flavors. We can either manually configure that one statically, so it's fixed, does not change, which is fine for small networks where hosts don't change that often. But as you can imagine, in bigger networks, if you had to manually maintain and record what IP addresses were used by each machine, that would be a bit of a pain. So as always, there's a protocol for that, and we will go to Dynamic Host Configuration Protocol, or DHCP. So sitting on your network is a DHCP server, and that will hand out IP addresses for machines requesting them, automating that process of assigning IP addresses to different machines. So these protocols, again, live in the application layers because they need to use the transport layer, the network layers that are underneath, to communicate to other servers on the network. We will be looking at other application layer protocols later on, but the main ones we're going to focus on for this week are, as I said, the DNS, DHCP and NTP, so a network time protocol. So how does your computer find out what time it is? So if you went back to the beginning of the internet, this was an identified problem. So how do I represent the machines on my network using a more human readable name rather than IP addresses? So you can see an example here. So this will be an example of a fully qualified name. Well, it's missing a dot, but a fully qualified name. So you've got your domain name, which in this example here will be desk85.lan, and you've got your host name, so Pi1. So this would be a common domain name for that desk, and then you'd have Pi1, Pi2, Pi3, for example. So if you see a name ending with .lan, that's on your local area network. But obviously, if we're trying to give meaningful names to machines spread across the world, spread across the internet, we want to start to think about organising those under common categories. So originally this was broken down into organisations and countries. So some sort of a location-based identifier. So rather than .lan, you could have the country code. So for example here, England was .uk, France .fr, America .us. So by just looking at that host name, looking at that domain name, you could start to see where that computer was in the world. In addition to that, there's also categories that give you an indication of the institution. So .ac, for example, for academic, .gov for government, .mil for military. And over time, these have expanded ever more. So some more descriptive ones down the bottom here. So .bank, .air force, and even .eurovision. These are all registered top-level domain names. And if you want to see a full list of those, you can go to this website to see what's out there. So back in the early days when the internet was small, one way of mapping a name So for example, www.york.ac.uk, the university's web server, to an IP address, was to maintain a list, was to maintain a centralized host table on each machine, a file. And as you can see example here on the Raspberry Pis. So we have the machine name and we have its IP address. So if we were to open up a web browser and we were to go to PyTime, you can see that maps that to an IP address. So that host name is resolved to an IP address by simply using this file. And it should still use today. So if you look on your operating system, be it Windows or be it Linux, you'll find a hosts file. And if you want to put into that commonly used host names and their associated IP addresses, that's one way of speeding up the resolution of a name to a number, a host name to an IP address. But obviously the downside of doing it that way is it's static. If the IP address was to change for some reason, owing to load balancing or machine crashed and it had to be replaced by a different machine, every time you were to use this host name, it'd be resolved into the old IP address rather than its new one. So things would stop working quite quickly. And as I say, that's the way we did do it back in the early days, the Whois registry. But obviously as the internet expanded, those mappings of names to numbers became more fluid, more dynamic, and more difficult to manage. So to overcome that one, as always, we need a protocol to do that. We need to automate this process. And that's where we get our DNS servers. So obviously we need someone to organize this for us, some institution that manages the assignment of IP addresses and autonomous system numbers. So IP addresses are used to identify our machines and AS numbers are used to identify each network within the network of networks that is the internet. So the main body that does that is IANA, and they subdivide that, as you can see in this diagram here, to a number of regional authorities or regional internet registries. And our particular registry of choice is RIPE, so the yellow one there for the UK, manages the allocation of our IP addresses. And another big player in these top-level domain name servers is ICANN, the Internet Corporation for Assigned Names and Numbers. Okay then, so the protocol that automates this process from fully qualified names to IP addresses is DNS, so our Domain Name System Protocol. If you'd like some more information on that, look at RFC 1035. Quite an old protocol, so first came about in the 1980s, so it's gone through a number of iteration improvements over the years. But basically it's a distributed database, a number of replicated servers that allow you to convert that name down into an IP address. So these servers are located across the world, so their data is replicated across the world, so that helps improve reliability, so removes any single points of failure. Obviously replicating these servers also means that they're closer to you, so reduces communication delays, and having multiple servers means that one server isn't doing all the processing. So this also reduces the loading on any one server. As always, it's a standard client-server model. The port used to identify this server is port 53, so you make connections to your DNS server on port 53, and this time we actually use UDP links, so the user datagram protocol. So I think this is our first example of a UDP-based protocol, and we'll look into UDP and TCP links in more detail as we go down the protocol stack, but for the moment, the thing to remember about UDP is it's a simple protocol, it's a quick protocol, and it doesn't matter if we lose some of these name resolution packets because we can always ask again. It's not like in FTP, so when we're transferring a file, for example, if we were to lose any one of the packets, that would be disastrous for that particular file. It would be corrupt. So that's why we use TCP for FTP communications. But for this one here, when we're just trying to resolve a name to an IP address, if that packet was to go missing, we could just re-ask for it. So there's no big advantage in going for a reliable link. We can use our unreliable UDP links. And as it says there, a lot of applications use DNS, so it's surprising how quickly a system will break and where it will break if DNS goes down. But as a general rule of thumb, if your system starts to slow down, I'd be looking at the DNS side of things. And we can see how we can do that later using the dig command in the lab. Right then, so how is this distributed database organised? Well, it's organised as a tree. So at the top, you have your root DNS servers that know their location, know the IP addresses of all the top level domain servers, and these servers know the IP addresses of all the secondary level domain name servers, and these know the IP addresses of the layers below them, so perhaps the authoritative DNS servers for a particular domain, and within that there'll be local DNS servers, caching DNS servers, that you may be using. So to see that more graphically, I have a diagram of that one. So maintained by ICANN are your root DNS servers. So that's the starting point for any DNS name resolution. So let's, for example, say you're at home and you want to access the machine identified by the fully qualified name vle.york.ac.uk. So that request will go to your local DNS server that will then query the root DNS servers. So it will ask the root DNS servers, does it know anything about .uk names? And the root server will point it to one of these top-level domains. So obviously it will point it to .uk top-level domain servers. So these DNS servers don't know the IP address that we're trying to access, but what they do know is somebody who knows about the .ac.uk servers. Again, this DNS server here will respond back to your local DNS server with the IP address of a server that knows a bit more. So again, your local DNS server will talk to this domain server, and eventually you will get to an authoritative DNS server. So an authoritative DNS server has that mapping between a name and an IP address. And this one here will return back to your local DNS server that IP address. So this is your start of an authoritative area. So an SOA, a start of authoritative area. And within this DNS zone, you could have multiple subdomains. So for example, cs.york.ac.uk. But these servers are responsible for resolving that query. So again, same process if you were to Google something. Your local DNS server would send out a request to the root servers. Do you know anything about things ending with .com? The root servers will return back to your local DNS servers the IP addresses of the top-level domain servers that know about .coms, and they would pass information pointing you into the right direction to Google's name servers. And these will be able to provide you with the IP addresses that you're looking for the particular name that you're requesting. So the thing to take away from this one is a multi-hop process. So it's not one DNS server that magically can resolve that query. You have to query a number of DNS servers until you find that authoritative server that does know that IP address. And if you want to have a look at that one in a bit more detail, there's a web page there where you can look at all of the top-level domain names, and there's quite a few. Obviously, there's a lot more than I could put in this image. Conceptually, logically, your root DNS servers are broken down into 13 DNS servers. So a.rootservers.net all the way down to m.rootservers.net. And to get you started, these are assigned to well-known IP addresses when you're doing your DNS queries. And any of those 13 root servers will be able to point you to the top-level domain server that you're looking for. Originally, at the beginning of the internet, most of these DNS servers were over in America, which, as you can probably imagine, when you were doing a DNS lookup from the UK to America, that took a few milliseconds, obviously slowing things down. But over time, these root servers have been replicated all over the world. Okay, so this raises a question. So if these top-level root servers are replicated across the world, what type of connection are we making when we want to connect to them? So to help you think about that one, a quick quiz. So we have 4 pictures here, A, B, C and D, and each one of these describes a particular way a host can connect to another machine across the network. They can be unicast, broadcast, multicast or anycast. So have a look at the descriptions below and look at the pictures and consider which picture is which. And then consider if we have multiple replicated root DNS servers. I think at the time of recording there's around about 1,865. What type of network connection should we use to connect to these? And as always, we'll go through the answers in the lecture review session. So a DNS query can contain 253 characters. So our domain name can be made up of one or more labels, and a label can be 0 to 63 characters long. So in the previous example, UK is a label, AC is a label, York is a label. And these labels can be combined together to produce your domain name. And if you took it to extreme and each label was one letter, you could have 127 subdomains. But typically we don't need that level of resolution. They're normally a lot smaller. www.google.com, for example. As I might have hinted a few times, to be a fully qualified domain name, you have to end with a dot, and that dot is referring to the root DNS servers. And when we use the dig command in the labs, we'll see various types of DNS records. We'll see some SOAs, start of authoritative areas, also some CNAMEs, some canonical names, some aliases, basically allowing you to map one name to another name for multiple names to share the same IP address. And you'll see that one if you do a dig on our mail.york.ac.uk, for example. So yeah, that's what we'll do in the lecture review session. We'll go through some various dig commands and see how we can look at the various names, how they're broken down, look at those roots, top level domains and authoritative domain name servers by using that dig command and have a little look at how things work. This one here I just found funny. Well, again, we'll look at it in the lecture review session. But again, just having a look around at how many different names are actually registered to somebody. Equally, you can do the other way. So with the dig command, rather than converting a name into a number, you can convert a number into a name. And forgive the joke. So if you dig, you create a hole. If you reverse dig, you fill in the holes. I feel like digging a hole, so I'll stop there. So again, in the lecture review session, we'll have a look at this. We'll have a look at this Python code that is calling the dig command. And it can be interesting to see what fully qualified domain names are assigned to each IP address. For example, in this list here, can you see my laptop, for example? Rightio, the scary bit. How is a DNS query structured? So what actually is sent across the network? So in general, DNS is structured in this format. So think of it as a generalized data structure that is used when you're doing a query or when you're using a reply. So it's a holder, it's a bucket of stuff that you can fill in with specific details as you need to transfer between your various DNS servers. So you've got spaces for questions, your queries, the responses, the answers to those questions, some information about the authoritative elements in your DNS network, and various additional stuff that you may need to pass. So it's always transferred in this kind of bucket of stuff across the network. So these various kind of predefined sections. So to start it all off, you have a header. So this header section here is broken down into these various fields. And obviously, because you can have one or more questions or these various elements, you need some field to indicate how many questions are within this message. So here you've got a 16-bit value, tells you the number of questions, number of answers, number of name servers, and a number of additional resource records. So your DNS packet here will have an ID, an identifier number. It will have some various flags to indicate whether this is query or response, what types of DNS queries you want to do, your response codes, if there's any errors. So all of that is in the header. So you'll pass the DNS server a query and you'll pass it the name, the fully qualified domain name that you want to access, the type of query, and the responses to these queries will be passed back as resource records. So using this format, as you can see here. Now, if that's not confusing, I don't know what is. But if you'd like some more information about that, obviously there's a web page for that one. So if you go to RFC 1035, you can find out some more information. And more specifically, you can look at the various formats on page 25. So here again, we in lovely ASCII art, we have the general structure of a DNS query. That is a message. Then we have our message header. So as you probably guess here, there's an awful lot of information and we're going to skim over quite a lot of it. So for example, if you read through this at the beginning, it states that a DNS name can be 255 characters long. So why did I say 253 in the lecture? Well, the answer is given here. So it all depends how you actually encode it within the message. So there's so much subtleties. So your fully qualified name is actually represented as counts and characters. So you provide a count, the number of characters within a label. You don't provide the dots, but you have to terminate it with a zero count at the end. So if you take into consideration the end and the beginning counts, effectively removes 2 characters, leaving you 253. But as I say, there's a lot of subtleties there, and do have a flick through, but don't be scared off by thinking that you have to know all of this protocol's functionality, because there's an awful lot. And for this module, luckily for you and me, it's just an introduction. So we don't have to go through all of this, but do have a flick through. Do start to think about what's going on in these various protocols. Rightio, to see this in action, we'll be doing some demos in the lecture review sessions. So we'll be capturing some DNS queries and taking a closer look at these various headers. So as previously discussed, here we have a DNS response packet. So you can see it's broken down into the various headers, the queries, answers, and here we have the response responding to the PI in our test system, giving it the IP address for a particular query. Obviously in the labs, our PI systems do not have access to the internet, so we can't access real-world name servers, but we do have a PI hole. So we do have a DNS server attached to our lab network that will resolve these names. And that's implemented using the software PI hole, which we'll have a look at in more detail in one of our labs. So a DNS query can be iterative or recursive. So what we have here is an example of a recursive DNS query. So your client requests the resolution of a particular fully qualified name. So in theory, you would send that to your local DNS server. That will then send this query onto the root server. That would send the query to the top-level.com DNS server. That would then pass it through to the Google DNS server, which is authoritative to that area, and that would then pass back the IP address to you. But that's not how it happens, because obviously the root server does not want to take control of the whole internet's DNS resolutions. So more generally, DNS is performed iteratively. So you get a recursive lookup to your local server. So you basically offload the DNS lookup to your local DNS server, and that will then iteratively go through and talk to all the other DNS servers until it gets an IP address. So rather than passing responsibility for this lookup to one DNS server and then transferring the responsibility to another DNS server, it's done by your local DNS server. So for us here at York, that will be 144.32.128.242 from memory. Or 243, I think there's two of them. And there are local DNS servers for the department. Again, another optimization to help spread that load around the various DNS servers. We tend to use round-robin DNS. So for example, when your local DNS server requests from the root server a top-level DNS server that can provide .com information, it will respond back with a list of various DNS servers that could answer that question. But the top level response will change every time you make a request. So it will cycle through a set of possible .com DNS servers for you. So you're not always hitting the same server every time. It spreads the load across a pool of DNS servers. And again, we'll see that in the lab when we use Dig on the lab PCs that are connected to the internet. So eventually, as it kind of shows here, your local DNS server will pass to you the IP address for the fully qualified domain name that you're looking for, but also what it will do is it will cache that IP address. It will store a copy for itself. So next time when someone else requests that lookup, it won't go out onto the net to resolve that. It will use its cached value. So obviously this raises the question, how long should it keep that cached value? And that's determined by the authoritative DNS server. So when it responds back with the IP address that you're looking for, it'll also attach with that a time to live field. That tells this server how long it should hold that IP address in its local cache before it re-requests that information. So the TTL value can vary. It can be a very, very long time, so thousands of seconds or maybe 300 seconds, depending on the priority. So the bigger the TTL value, the less frequently it will bother the Google name servers. But this could mean if one of the Google servers goes down, we'll still be requesting an out-of-date IP address. So it's a balance of how frequently you want people to access your name server and how quickly you want to recover if anything goes wrong. So hopefully we start to have a think about how the network works. So we've looked at some of the protocols in the application layer, so HTTP, FTP, SMTP. We're starting to look at some of the RFCs. So we've looked at the DNS RFC. We're starting to think about how we identify hosts on the network. So we've got a fully qualified domain name, so a human readable description of what that machine's functionality is and perhaps where it is in its world. So you can see here, for example, here we have the name of a machine in my office. So you can see it's in the UK, it's at York University, it's in the computer science department, and it's my student development machine. So it runs an image of the machine that is in the lab. So in this lecture, we start to introduce the ideas of DNS. I say we'll expand upon those a bit more in the lab. But then this then raises the question, okay, I can give each machine a name, but if that machine then wants to find out the IP address of a particular web server, how can I make a DNS query if I don't have an IP address? To find someone else's IP address, I've got to have an IP address myself. So how do I get that in the first place? So one solution to this problem is to use static IP addresses. So in each operating system, there's different ways of doing this. But here's an example of how you would do it in some Linux-based systems. I confess perhaps a little bit old hat with the advent of systemd, but we still do it this way on the Raspberry Pi. So in the file /etc/network/interfaces, you'll find descriptions like this. So for the Raspberry Pi, E for 0 is the onboard NIC. So we're saying this interface is it's an internet and it's static, and you start at the IP address, and in this example here, 192.168.0.254. We also can pass additional parameters. We haven't talked about network masks yet, subnets, etc., gateways, but everything you need to know about how to connect to the network you can define in this file, and it's fixed. It does not change. Now, the advantage of that on small networks where you have complete control, where you are root, then this is a very easy way of doing things. Like I say, on these small networks, things don't change that often. There's only a few machines. So statically defining each host's IP address is as good as any other solution. But as you can imagine, as your network gets bigger, so you go from perhaps 10 machines to 100 machines to 1,000 machines, manually maintaining a list of IP addresses becomes a little bit too much fun. And again, especially when you've got machines joining and leaving networks, which you would have on wireless networks. So we need a different way of doing it for these bigger networks, and that's when we move over to DHCP. So as always, we have an RFC for our protocol, so RFC 1541 if you want to have a bit more information about what the DHCP protocol does do. DHCP created in 93, but based upon an older protocol, so BootP, developed in 1985, RFC 951. And we'll see that in the lab. So when we're using Wireshark and we want to filter out DHCP packets, the protocol we actually enter in the filter box is BootP, and that will also filter out your DHCP packets. So as always, client-server model, so your server will be listening for DHCP requests on port 67, and your client will be listening for DHCP server responses on port 68. Communication is connectionless. It's using unreliable UDP links again. As we can just keep sending out those DHCP requests if we were to lose some. So when your client initially wants to request an IP address from the DHCP server, obviously it doesn't know the IP address of that DHCP server, but it will assume it's on the local network, so it will do a broadcast. So therefore it uses the broadcast address 255, 255, 255 and 255, so all ones. So it'll put out an IP address of all ones onto the network. So all hosts on the network will receive and process that packet. And hopefully you've only got one DHCP server, or otherwise you get a bit of a race condition. But the DHCP server processing that all one's IP address will notice that the destination port is 67. So it goes, all right, that's for me. So it will start that DHCP process. Obviously, in that packet going out with that request, the client needs to specify an IP address and what port it will be listening to for the responses. So initially, it doesn't know what its assigned IP address will be, obviously. So it puts all zeros in, an undefined, an unknown IP address, and port 68. So it's saying to the DHCP server, I'll be listening for your responses on port 68. And these are special IP addresses, reserved IP addresses, as defined in the IP protocol. And as always, we'll be looking at that protocol a little bit later on. So if all goes to plan, the DHCP server will give the client an IP address, and that will be leased from the DHCP server for a certain amount of time. So 600 seconds, 10 minutes, or a day, 86,000 seconds. Very much depends on how you want to set up that network. And what type of machines you've got connected to that network. So if they're hardwired to the network, do you need to be asking repeatedly for an IP address? Probably not, so you'd make it quite a big value. But if you had a Wi-Fi network where machines come and go frequently, you probably want to make the lease time smaller because machines will be coming and going, and you don't want to run out of IP addresses. You've only got a certain pool of IP addresses that you can lease on that DHCP server. As it says there, to play a bit safe, the client will try to renew the IP address after about 50% of the time has elapsed. So it won't wait till the last minute, try and release that IP address. It'll start doing that halfway through the lease time. And obviously it will try to request the same IP address. It'll try to renew the IP address that was previously allocated. And if all's going well, the DHCP server will do that. Obviously, if things go wrong and the DHCP server goes down or stops working, then no one will respond to your request for an IP address. In that scenario, you'll be allocated an IP address from a specific pool of IP addresses starting with 169.254. And the process doing that is defined in this RFC. So from memory, if the client doesn't get a response, the lower 16 bits is determined by a pseudo-random number generator. And obviously each client will have its own seeded value, so they'll generate different random numbers. So it'll randomly choose the lower 16 bits. I say the top 16 bits, the 169.254 is fixed. That's always the same. The lowest 16 bits will be random. And as I say, I'll have to check this, but from memory, it will probe the network to see if that randomly chosen IP address is actually already existing on the network using the ARP protocol. Okay, so what does a DHCP protocol packet look like? So like DNS, it's predefined data structure, a template, a bucket of stuff that is used to carry all the information between the client and the server. So this is the general structure you can see here with these various fields. So what you've got is a header, you have a unique ID, so to identify DHCP packets that are involved in the same DHCP transaction, they'll all have the same identifier, so you can see here. And then we have various fields here which get filled in as you go through that process. And as I said, this template, this data structure has to handle different scenarios, not just the DHCP process we're looking at here, but obviously how do we do a net boot? So that's also kind of in there. Equally, the general assumption is that your DHCP server will be on your local LAN on the same subnet, but it doesn't have to be. So how do we handle scenarios where your DHCP server is on a different subnet, is on a different network? How do we specify relay agents to pass on that data to a different network? And that's all within this structure. So as you probably guessed, if you want to know more, then the place to go, as always, is your RFC, so RFC 1531. So if you scroll through here, this will explain what all those different fields do. So again, as always, we have our ASCII art representation of the various fields within our data packet. And if you want to know what each of these fields represents, then that is obviously defined here. So you scroll back down here. See here a short description of what each of those fields represents. So as I was saying, the XID, that random number that identifies the particular DHCP transaction is specified here. Or if your DHCP server is not on the current subnet, then you'll need an IP address of your relay agent. I do confess, I have never set up a system which uses such. All my systems, the DHCP server is on the local subnet. But if you wanted to find out more, as always, it's in these documentations. So here we have a sequence diagram of a client and server interacting. So here we have our client, here we have our server. So you can see time progressing as you go down, and the arrows show the various packets that are transferred from the client to the server, and equally from the server to the client. So the DHCP process is broken down into 4 phases. We have discover, offer, request, and acknowledge. So initially the client puts onto the network a broadcast packet, and the key things to identify in that packet are shown here. So it's tagged as a discover. So if you look in the option field, there'll be a code that identifies this is a discover packet. So it's looking for a DHCP server. It's saying its IP address is not known, so it's all 0, but it's listening for responses on port 68. The destination address of where it's going to is a broadcast address, so all 1s, going to port 67, which will be the DHCP server. It's saying that my current IP address is empty, it's all 0s, and I have set a random value, an identifier, to this random value here. DHCP server will receive that. It's a broadcast packet, so it'll process it, identifies it's for him. It will identify it's a DHCP discover request because it's going to port 67, so it will send back an offer. In that packet, obviously the source address is the IP address of the DHCP server. Again, because the client doesn't have an IP address at the moment, it'll be a broadcast address, so all 1s, but going to port 68. The client can identify that this DHCP packet is for them using the ID value, so obviously these will match. And it can grab the allocated IP address. So this is what the DHCP server is offering as a lease. Again, in the option fields, this packet will be tagged as an offer. It will also have additional information giving you the IP address of the DHCP server, the lease time, and any other additional information it needs. At this point here, this is not allocated to the client. The client has to request this IP address, goes, yeah, that's good, I'll take that, thank you very much. So again, it will transmit a packet onto the network. Again, it'll be a broadcast saying, thank you very much, I'll take that. But as it says there, I believe this one here can be the IP address because obviously it'll identify from the offer packet what the IP address of the server is. So this may be a unicast rather than a broadcast. The DHCP server will receive this and go, right, goes, okay, right, the client wants that IP address, I'll reserve that for them, and it will send back now a acknowledge packet saying this IP address has been reserved for you, you're good to go. You can use that IP address for that, obviously, that specified lease time. And obviously halfway through that time, the client will repeat this process to renew that lease. Okay, demo time. So in the lecture review session, we'll have a look at that. So in our Pi system, Pi 1 is a DHCP server. So that leases IP addresses to Pi 2 and Pi 3. So if we go through this process, we can actually see this in operation. And we can see that data structure being filled up with the various fields during that discover, offer, request, acknowledge cycle. Actually, if you look here in the Wireshark catcher, we can see there's a DHCP release there. So that's when I executed the DHCP client release command. Say I'm giving up that IP address. So this command here releases the allocated IP address, and down here I re-request it, and it's getting that IP value back. And as I say, we'll look at that in the lecture review session. Okay, the final protocol I want to look at today is NTP, so our network time protocol. So RFC 958, again an old protocol, which has also gone through a series of revisions. Client server model, connectionless, UDP, same as DHCP. Well, obviously the server is listening on a different port. It's listening on port 123, which is a nice port to remember. So typically your machine at home will be getting its time from your home router, and your home router will be synchronizing its time to a pool of NTP servers on the internet, as you kind of see listed here. So here we're looking at the various NTP servers that my PC is interrogating to work out what the time is. Because obviously the problem is, when you request a time from an NTP server, you don't know how long it takes for that information to get from the server to you. So by the time it gets to you, it's out of date. So you have to do some sneaky stuff to calculate the latency of the network communication. And just for fun, I would like you to go out and have a look at that protocol. So I would like you to look at RFC 958 and see if you can work out how NTP works. So how does it calculate the network delays? What format does it use? So how does it represent time? On our network, we'll have a number of NTP servers, and they're all allocated stratum levels. Our highest accuracy clocks are based on atomic clocks. For example, those timing devices that are in GPS satellites, for example. So really accurate clocks. So where do these live in our NTP hierarchy? What is stratum 0? What is stratum 1, 2, 3, 4 going down that hierarchy? Can you identify what these levels indicate? Also, if you're using a Linux system, you've got your NTP command line tools. So if you enter the command NTP Q-P, you'll get some additional information, as you can see here. So what do all these fields represent? So you can see here, we've got pole, reach, delay, offset, jitter. Have a read around there, see what you can find out. And obviously, if you want to know more about this command, you can use the man command. So you go man NTPQ, and that will give you some additional information. Obviously, this is not wasted time. In a lab, we will be looking at the NTP protocol in a lot more detail. So it's good background reading for that lab to come. So do have a look. Do have a read through that RFC. I know it's big, but do have a read around. See if you can get the gist of how that protocol works, because you'll need that knowledge when we get to the associated lab. Okay, so in this lecture we looked at some of the background protocols. We looked at some of the housekeeping protocols that bind things together. See what I did there? DNS bind. Another classic joke. As I said in the lecture, don't get too worried that you'll need to know the minute details of all these different protocols. As I say, DNS, DHCP are relatively big protocols, and there's lots of nuances and subtleties there. I'm not expecting you to know all of that, just a basic understanding of what they do, and that's what we're looking for in this module. And you will get some hands-on usage of DNS and DHCP in the lab. So you'll actually see those packets being transferred between the clients and the server using Wireshark packet captures. Obviously, we can't see a true DNS lookup. We won't be accessing the raw root servers because our network's not connected to the internet. But we do have something that simulates it. We will be using Pi-hole and a caching DNS server in our Pi system. So when you do a DNS lookup on the Raspberry Pi, it will first interrogate the router that is in your system, so the MikroTik router. That is set up as a caching DNS server, so it will return the IP addresses of each Raspberry Pi in your local system. If you want to know the IP addresses of Raspberry Pi systems on another desk, then it will transfer that out to Pi-hole. So it'll go onto the lab network to interrogate our lab's DNS server to get those IP addresses. And again, you can capture those packets in Wireshark to see that operation happening. Again, we're pushing down the network protocol stack, so hopefully some things are starting to become clearer. As we've looked at some of these application layer protocols, I've sort of glossed over how they're communicating across the network. So now we'll be moving down to our transport layer. So we'll be looking at TCP and UDP protocols and seeing how they differ and where they're used and why they're used and why they're needed. And as always, we'll be pushing down that protocol stack until we get to the lower physical layer, right at the bottom there, layer 1. In addition to the work we'll be doing in the practicals, if you'd like to build your own network systems, there's some examples here. So if you go to my homepage, so if you go to simplecpudesign.com and go to the networking section, you'll find links to the various servers that you'll be accessing in the labs. So we have our time server, our NTP server, and our DNS server, our name server. So if you follow these links through, you'll see how these systems are built. So the NTP server, the time server, uses a GPS receiver connected to a Raspberry Pi, and that is used to synchronize the time to the machines in the lab. Because the lab network is not connected to the internet, it doesn't have access to the internet's NTP servers. But you can create your own if you wanted to. So you can create this beastie here. That sits on my windowsill in my office. So here we have the GPS antenna. The receiver is in this black box here. Here's our Raspberry Pi. I've got a little LCD display here. The big aluminium sheet is our ground plane. I found they work better on a ground plane, so you don't necessarily need this big sheet. But I was picking up a lot of interference for some reason. So by mounting the antenna on this ground plane, it improved its reception. So it's a bit of an easy win. So that's what I did do. In addition to our Raspberry Pi based NTP server, we have a DNS server, a name server. So again, build out a Raspberry Pi running Pi-hole. So again, talks you through how this is set up and how to install Pi-hole on a Raspberry Pi. So if you've got a spare Raspberry Pi at home, this is a pretty minimal project. All you need is a Raspberry Pi connected to your local network and you can set up a name server. And the advantage of this one here is it will block advertisements in your web browsing and block bad websites from your internet browsing. So again, do have a look at that one if you would like to set up your own Pi-hole. Okay, I think that's where I'll leave it for the moment. And as always, we'll continue this journey in the next lecture.